Hello everyone, we are back with our aerodynamics lecture. So today we will discuss about the compressible flow through nozzles, diffusers and wind tunnels. So this is in chapter 10 in Anderson's Fundamentals of Aerodynamics book. In today discussions we will be focusing only on the compressible flow through nozzles. And in the next sections, in the next meeting, we will discuss about diffusers and wind tunnel. So, because uh, the basics of compressible flow through these three different equipments is based on the applications of compressible flow through nozzles. So the basic knowledge is first we need to learn about the flow behavior of a compressible fluid in a nozzle. Therefore, we can proceed with the flow in a diffusers or in a wind tunnel. So wind tunnel in these terms will be sonics or supersonics or hypersonics wind tunnel. So it's a high-speed wind tunnel with a pressurized air. It's a difference than the normal wind tunnel or subsonic wind tunnel that we discussed earlier this semester. To begin with this topic, we need to understand the needs of having a reliable testing mechanism, since we cannot, let's say that we are trying to develop an aircraft, we cannot directly create a 1-to-1 scale of the aircraft or a real scale of the aircraft and put it in the atmosphere and then test it directly in it. First, we need to create a model, and then we need a place to test this model, right? Therefore, we need a wind tunnel. Since aircraft, especially jet fighter, for example, able to fly in a higher higher than a sonic region, we need an equipment or tools to examine the model of this aircraft as close as possible to its sonic region. Therefore, the idea of this supersonic wind tunnel came to. On the other hand, most of this supersonics aerodynamics data, first step to do the research is in the wind tunnel on the ground. So we put the model here in the test sections, and we generate the flow that as close as possible to the real applications in sonic flight, for example. And therefore, to be able to understand the design, for example, of a wind tunnel and a nozzle, the aerodynamics fundamentals for this compressible flow is an important things to learn when we want to design properly wind tunnels, rocket engines, or lasers or jet engines, and so on. What makes them have something in common between jet engine and the wind tunnel here as a supersonic wind tunnel, that they have this nozzle look profile here. If we see from the side view, first it has a higher or a bigger area, cross sections area here at the inlet, and then along the flow the cross sections is getting smaller, and then it's getting bigger again at the end of the wind tunnel. That's a brief introduction about the nozzle design, so we will know later on why it has these smaller sections in the middle of the wind tunnel. Let's say that we have a geometry that looks like a bottle like this. It has a neck, and we consider the flow is changing in the x directions, and the area of the flow geometry is changing in the x directions also. So area is a function of x also. And we also need to consider the components in y and z or z, for example. However, these two components in y and z directions are smaller than that of in the x direction. So it's safe to say that they are negligible when we compare it to the x direction, where the main flow pattern is in the x direction. So therefore, it's a 3D phenomenon, but as the x directions is as the x direction is more dominant than the two other directions, we call it as a quasi one-dimensional flow. It looks like a one-dimensional, but it's not one-dimensional. Therefore, it has y and z component also, but we somehow can assume that it's only x that working on it. And we still need to work with these three governing equations or conservations. This is the continuity, momentum equations, and energy equations. So from here we can see that the H0 or the total enthalpy is constant throughout the system. Assuming that we have a flow in a small control volume between region 1 and 2 here with the line of dx, and it has a property prior to region 1 of pressure, area, velocity, and density, and then after leaving the area or region 2 we have change in pressure, change in area, change in velocity, and change in density. Therefore we can rewrite those three momentum, energy, and continuity equations in a differential form, since we have a change in those properties. So this is the differential form of continuity equations, this is a differential form of momentum equation, and this is the differential form of energy equation. So rearranging these three equations, we come across with these new relations between changing in area, dA, divided by the earlier A, is equal to the Mach number to the power of 2 minus 1, and multiply with the change in velocity divided by the velocity at the inlet. So this equations is basically what we need to able to understand in order to design a nozzle, for example. So this is, we have two types of different nozzles. So we have this one is convergent because it's a smaller, getting smaller, and then this is a divergent one. So therefore this is called as a convergent divergent nozzle. And the other one is the opposite one. This is a divergent and convergent nozzle. Now assuming that we have a subsonic flow incoming to the nozzle, so means that the Mach number is lower than 1. Therefore, if we have Mach number lower than 1, this part of equations will become negative. Therefore, the higher the velocity coming in, we will have a decrease in the area, or a negative dA. Therefore, the higher, as we increase the velocity, du, change in velocity, and this part is negative, we have a smaller or negative dA, and then the area is getting smaller here. That's for the case when we have a velocity coming at a subsonic level. Therefore, then a decrease in the velocity is associated with an increase in area. That's if we increase the velocity. That's here. After leaving this area, where the velocity is getting smaller, and then we suddenly increasing the area, and then the velocity is decreasing. So it's a basic of this continuity equations, where we have functions of velocity and area, cross-sections area. So for a subsonic compressible flow, to increase the velocity, we must have a convergent duct. A duct here, this is a convergent one. And to decrease the velocity, we must have a divergent one. And this also applied to the incompressible flow that we are discussing at the moment. So remember that these terms only apply for a subsonic region where we have Mach number lower than 1. As an opposite to the previous design of nozzle, now we come to the divergent and convergent type of nozzle. For example here, assuming that we have a supersonic flow where the Mach number is higher than 1, if we have Mach number higher than 1, then this part of equations will become positive, as the Mach number is functions of velocity also, meaning that if we increase the velocity or du, we will also have an increase in dA, or change in area here. So one way to increase the velocity in a supersonic region or supersonic flow is to have a increase the area, cross-section area, and the other way around, to decrease the velocity we also need to decrease the area, and vice versa. Since it will flow into a geometry, therefore we can control the geometry, whether we want to increase the area or we want to decrease the area. That's for the supersonic flow where the Mach number is higher than 1. And what if the flow is in sonic conditions, or m equal to 1, and this will become 0, and then du will be infinite. Let's see the further explanation for this part in the next slide. Let's assume that we have a gas or a fluid at a rest, and it has isentropic behavior where entropy is constant, so S is constant across the nozzle design here. And then the gas accelerate through the convergent duct, so the incoming flow is a subsonic one. And then right at this region, or they call it throat, the Mach number become 1 as the velocity is increasing. So the exact point where the Mach number equal 1, or sonic region, is called throat. So as soon as the sonic conditions are achieved, we must further increase. Remember from the previous slide, if we have the velocity is increasing, and then we need the flow to leave the nozzle at a supersonic region. Therefore, we need to increase the area. Therefore, we call it a convergent divergent duct. And the minimum area to have the sonic region is called the throat region. As you might still remember, then from the last chapter, we use this asterisk or stars notes and the upper scripts of the properties of the flow to show them that the flow is at exact sonic region, so the Mach number is equal 1 at this region. So we know that if Mach number equal to 1, then the velocity is equal to the speed of sound, of course. And then by using the continuity equations, we know that these properties remain constants across the nozzle. And one particular equations that we can use is the area Mach number relations. So it's the ratio between the area at one point here and the area where the Mach number equals 1. So m here is the Mach number of this particular area. So you can take any slice, not just this one, and put a there, m and u, and then we can apply these equations on it. Therefore, so we see here that the a for a throat is only a function of x and Mach number then again, and also the Mach number is also functions of x. So this is assuming that we have a subsonic flow incoming to this nozzle, and it has a P0, T0 at the inlet and U at the inlet, and then suddenly at this throat the Mach number become 1, and then increasing the area to increase the Mach number even higher. And we can see here, after passing Mach number equal to 1, by increasing the area, the Mach number is also increasing. But we need to remember that by increasing the Mach number, the pressure ratio is decreasing, and also the temperature, static to total temperature ratio, is also decreasing. So we can have a look at the Appendix A of the Anderson books to find the value of P per P0 at certain Mach number. And also we can use these equations to get the ratio, of course, at a certain Mach number. And this is only valid for a subsonic region at the entrance. And we know that in the nozzle, the phenomenon is isentropic, therefore S is constant, entropy is constant. And we know that at the exit, the Mach and pressure, the Mach number and pressure is ME and PE. And we need to remember that it has to reach the, so if you look at the book, it's called as the MA6, so it's the isentropic Mach number. So at the exit, the Mach number has to be equal to this isentropic Mach number. And also the same apply for the pressure. So pressure at the exit is also has to be equal to the pressure of the isentropic, or PE6. That's also applies to the temperature. It's also TE6. We need to remember that the pressure difference between inlet and exit, this delta P, is one of the driving force of the flow to occur. So because we have pressure difference, then the gas flow through. And then what if the pressure difference is not that large? Let's say that PE is like 0.99 of P0. That's the conditions here. At this point, since we have a very low pressure difference, the flow is a subsonic across the flow, across the nozzle, and then we have this Mach number 1, and then the flow remains subsonic after leaving the nozzle. And this is the point where the P exit is not equal to the P exit of PE6, or the P exit isentropic P exit, so to say. And then we decrease again the pressure. Let's say now we have 0.92 here, and then we have this Mach number profile across the nozzle. It's still below the supersonic or the isentropic Mach number. And then we increase again the pressure to this third time to a lower point, let's say 0.91 or 0.89, and then by reducing this, we have the exact sonic region at the throat of the nozzle. And then decreasing this pressure continuously while we still having the Mach number equal to 1 at the throat, it can create the phenomenon called as a choke flow. Choke, like being choked on your neck. So by keeping the mass flow rate constant and then reducing the pressure here at the outlet, so it's like disabling the communications between the throat and the exit then at the end. And then we have the choke flow, where the pressure at the outlet is decreasing. However, the inlet condition is not at the same following the reactions of the exit. Therefore, we have this choke flow phenomenon. On the previous slide, we see if the pressure at the outlet or at the exit is smaller than the isentropic pressure, or this P6. What if now we have the pressure is higher than the isentropic pressure at the outlet or at the exit? If the PE is higher than the PE6, a normal shock will appear at the exact point of the exit of the nozzle. And we can see as the Mach number is increasing, and at the throat we have the sonic phenomenon, and as you remember that at the sonic region, if we keep increasing the area, we will increase the Mach number also. But however, since we have a normal shock here, the Mach number suddenly getting lower due to the normal shock, because we know that across the normal shock the Mach number is decreasing. Therefore, they call it MA6 is the isentropic Mach number, and then MA5 is the Mach number at the exit of the nozzle. The same also applies to the pressure. There's a pressure spike here, suddenly increasing because the normal shock. We know that across the normal shock the pressure is increasing. And we have the subsonic region again after leaving the shock or leaving the nozzle. So up to this point, we have only discussed about the pressure at exact exit of the nozzle. Now, what if we also discuss the region outside the nozzle, where the pressure is called as the back pressure? So if the back pressure is smaller than the pressure of the exits or the surrounding, and we might have this shock interactions. And if you remember, then the shock will become an oblique one here. That's if the pressure at the exit region is smaller than or bigger than the isentropic pressure. We have an oblique shock at the exit. And the case where the back pressure, the surrounding pressure is higher than the isentropic pressure, it's causing the exit pressure to be higher than the pressure of the region. Therefore, we have an oblique shock. So you need to remember the sequence: isentropic pressure, back pressure of the atmospheric, and the exit pressure of the nozzle. If it's arranged like this, we will have an oblique shock at the outlet. Now, what if we have the exact value of the back pressure equal to the isentropic pressure? Nothing will happen. We will have a smooth flow leaving the nozzle. And if we have an isentropic pressure if the pressure leaving the nozzle is higher than the back pressure, or the isentropic pressure is higher than the back pressure, we will have this expansion wave here instead of an oblique wave here. So that's the arrangements of the pressure at the outlet causing the shock wave at the outlet. Now let's work on a sample problem where we have a flow through a convergent divergent nozzle. So it looks like this. And the area between the exit, so A exit per A throat, is equal to 2, and the reservoir pressure and temperature are 1 atm and 288 Kelvin. So P0 and T0 are this. So we need to find the Mach number, pressure, and temperature at both the trough, so at the asterisk point, and at the exit, where the flow is supersonic at the exit. So we have M higher than 1 at the exit, and the flow is M less than 1. So how do we solve this? So let's see on the next slide. First of all, we know that at the throat the Mach number is equal to 1. And then we know that the pressure is equal to pressure at Mach number equal to 1. We need to find the ratio between the pressure at the throat and pressure at the inlet to get the pressure at the trough. So therefore we need to find this at the appendix A of the book, where the Mach number is equal to 1. Therefore we can get the pressure at the trough. Also the similar apply to the temperature. We need to find the temperature at the trough. So this is the ratio from the appendix A, and this is the temperature at the inlet. Then we get 240 Kelvin. And also at the exit, since we know that the ratio between the area at the exit and the trough area is 2, we find the Mach number from appendix A again. It's 2.2, the exit Mach number. So it's increasing from 1 at the throat become 2.2. And then we need to find the exit pressure, right? So we need to find the ratio between the pressure at the exit and the entering pressure. Is also from the appendix A. We know the ratio is 1 per 1069, and then it's 0.0935 atm at the exit. And also same for the temperature, we need to find the ratio from the table also, and then we get 146 Kelvin. And the same also apply if the flow is subsonic. We need to find, we are being given that the Mach number is equal to 1 at the trough, and then we know that if the trough conditions is sonic conditions, we have the pressure at 0.528 atm and the temperature is 240 K. And at the other locations of the nozzle, the flow is subsonic. So therefore, at the area ratio of 2, for look at the appendix again, if the flow is subsonic, we will have Mach number equal to 0.3. And then from that we can see the pressure ratio and the temperature ratio also to get the pressure and temperature at the exit.